Right, so here we go. Yeah, thanks again to everybody's joining us today. Good evening, good morning, good afternoon. If you don't know me, my name's Joseph Guyan. I'm the digital product manager at ANSA Data Analytics. I've been working with casehole logging data now for about 20 years, with most of them spent recently here at ANSA. Over that time, I've worn a few hats, from analyzing the logs themselves to managing the analysis team. And just recently, as part of my job in business development and software sales, I've been running these webinars, and I think it's probably one of the best parts of the job. It's really fun. It's nice to meet everybody and have a quick chat with you all. They're a great chance for you to learn something new, get familiar with what we do, and just ask us questions, see what you can take away from these webinars. So, on that note, just a quick housekeeping point. We are recording the session. He says, yes, we are. And for that reason, we'll keep the questions and answers until the end, so I can stop the recording and we keep the questions and answers amongst ourselves. So if you do have any questions as we go, just pop them into the chat and we'll come back to them at the end. One thing I'll say at the beginning is I've asked for a little bit of forgiveness. This is quite a broad topic and we're going to be diving in quite quickly. So the introduction is going to be pretty swift. So if you're a beginner, bear with us and you can come back to me anytime if you're looking for a bit more in-depth. And the guy you want to speak to and ask those questions to is Faris Terai. He's one of our senior data analysts at ANSA. So I'll let him introduce himself to you guys now. I take the please do pick his brain at the end of this. He's somebody I always like to pick the brain of. So Faris, would you like to say a few words just now?
Yeah, sure thing, Joe. Well, hi everyone. First thing, thanks for joining us today for this webinar. As Joe said, I've been working for almost a decade on well log analysis and especially on cement evaluation and pipe inspection logs. And speaking of cement, it's our topic today, so it's quite convenient, I guess. So yeah, enjoy the show and we'll talk to you right after Joe's intro.
Okay. So I'll spend just 5 minutes setting the scene for everybody. Let's see what we got first of all. So very simply, we'll just talk about what is cement doing in your well? Why is it there? It's all the well integrity and zonal isolation, and some examples of why it could fail and their consequences. We'll talk a little bit about how to evaluate cement, concentrating on sonic logging methods and what they show. We'll ask ourselves what makes it difficult, what are the limitations of logging tools and any real-world obstacles that we might have. What do ultrasonic tools add to this? This leads us nicely into the example that Faris is going to show us about, which will be concentrating on the logging tool that we've seen quite a lot of lately, the Nusonix from Cereus Ultrasonics. We'll talk a little bit about that and what it's bringing to the show. So the role of cement, very simply, again, this is going to be a very quick version of it, but in oil and gas wells and geothermal and various other wells, where does the cement go and what role does it play in well integrity? It's a broad topic. This is very, very quickly, the cement is placed in those spaces between the well casing and the borehole wall, and sometimes between other concentric strings. Its purpose is to seal and support the well. It stabilizes the well, ensuring several critical aspects of isolation, and ideally it continues to function in that way for decades after completing the well. So what can happen if it doesn't go all to plan? So perhaps the cement itself doesn't bond properly to the casing or to the formation wall. Perhaps it degrades over time for various reasons, and the consequences of that can be severe. So, example, the produced fluids could migrate between zones downhole, or perhaps it can migrate to surface or into freshwater aquifers. Cement failure itself can manifest in several ways, which affects production, safe operation, and preservation of the environment. So evaluating cement bond integrity really isn't optional. If managing your well integrity can be seen as a license to operate, and that's what leads us to the technologies that we're discussing today. So why is it so hard to look at? It's kind of obvious, but once it's in the well, you can't look at it. We can't inspect it directly. So we generally rely on acoustic logging methods to evaluate how well it's bonded to the metal of the casing and to the formation wall. And the most widely used method is the cement bond log, or CBL. Again, another big topic on its own. You can run a week's training course on this. We're going to brush over it very quickly, but I'll just say that for the moment, these tools measure how acoustic waves travel through the casing. Specifically, it measures the amplitude of the signal traveling down the casing, which gives quantitative information about the cement casing bond. And another aspect of that measure, the variable density log, seen there on the right of that image, that provides information about the cement to formation bond. So using the VDL and the amplitude log together helps you evaluate the condition of the cement in your well. Now, why is it difficult? There are various reasons again, but partly because the cement placement perhaps itself can be imperfect. The casing perhaps is off center, so you've got different spaces on either side of it, meaning perhaps that the cement can take the path of least resistance as it's placed. Over time, you might develop very small gaps, so microannulus, you'll hear that phrase. These tiny gaps can allow fluid migration. The conventional CBL and VDL tools only measure acoustic signals averaged around the casing. So that means that if 80% of the casing is bonded, but 20% has a vertical channel, the average response might give you the picture of a good bond. There is some nuance there. That's a pretty simplified version of it, but you also have different sonic tools like segmented and radial tools, and they can give more details about the variations around the circumference. In general, when using CBL and VDL alone, you don't get the full picture. So that's why you might want to consider adding something else to your toolbox. So that would be ultrasonic inspection. These tools emit high-frequency pulses and measure the reflected signal at the casing and cement interface. Fundamentally different is the ability to scan the full circumference using some form of a rotating sensor. So you get the part of your result is a radial map, which highlights in greater resolution where the contact is strong and where it may be poor. This is useful for identifying features like partial bonding or perhaps channels that might not strongly affect the average signal in a sonic log. It doesn't replace the CBL or VDL. Sonic tools are still widely used, but when localized defects matter, for whatever reason, for regulatory, environmental, or operational reasons, then ultrasonic methods can provide complementary detail. And the table on the screen there shows you a combination of why you might want to run them in combination. Choosing between them basically depends on the objective, your well conditions, and the required resolution of your result. In many cases, the best insight comes from integrating both approaches. So with that, I will hand over to Faris. I'll just say hello to all these people who are joining in the first few minutes. If you have any questions about what you missed, just pop them into chat, and I'll hand you over to Faris now.
Great. Thanks, Joe. Yeah, like you introduced the tool, or you hinted to the tool, the Nusonix tool. Let's first start with a proper introduction of this technology. I guess it's convenient for us today. Well, it is an ultra-high bandwidth ultrasonic tool developed by the company named Cereus Ultrasonics Limited. The tool operates in virtually any liquid or pressured gas environment, and it's compatible with pipe sizes ranging from 278 to 1338. Like other tools on the market, it delivers both pipe inspection and cement evaluation capabilities. For the principle of measurement, straightforward here. You can see in the first part of the image on the left-hand side. So we do have an ultrasonic transducer that emits a high-frequency sound wave towards the inner wall of the pipe. And a part of that wave is reflected back to the transducer while a smaller portion transmit into the pipe material, whether it's steel or another material. The wave then continue to bounce between the inner and the outer wall of the pipe, gradually losing energy with each reflection. These multiple echoes we're seeing on the right-hand side part of the image. So these echoes are captured and converted into the frequency domain, allowing us to accurately calculate the thickness. In the next slide, we can see in a bit more detail how the signal looks like. Yep. All right. So in the top section, number one here of this, so in the top section of this image, we can see the full ultrasonic waveform where individual reflections are clearly defined, thanks to the tool's very high bandwidth signal. And right below number two, this is the envelope of the decay rate. So within the resonance window, highlighted in red in image number one. So that envelope is the decay rate of the reflections occurring at the casing cement interface. This decay behavior is what really allows us to determine the bonding. Finally, number three, in the bottom section, we see the signal transformed into the frequency domain. Notice the multiple harmonics captured by the Nusonix tool. And the spacing between these harmonics is what really what we use to accurately compute the pipe wall thickness, as explained in the previous slide. For the next slide, there's a comparison between the Nusonix and what we call the conventional ultrasonic tools. So on the left-hand side, it's is the conventional tools, and on the right-hand side is the Nusonix. So in the top half of the image, which represent the time domain signal, you'll notice that the first reflection in the Nusonix waveform has a narrower bandwidth. However, when we move to the frequency domain, we actually see a broader and richer frequency band available for analysis, which really gives us much more to work with in terms of resolution and accuracy. Same observation applies to the echoes in the lower part of the time domain view. Yeah, these are recorded right after the initial reflection, like I mentioned, the resonance window. Here you can see clearly how well defined and distinct the back reflections are in the Nusonix signal, especially when compared to, I would say, more blurred or merged echoes coming from the conventional tools. If you can give me the next slide, Joe, I'll talk about the outputs. What the Nusonix gives us for the cement part. Concretely, the Nusonix tool offers two options for cement interpretation. On the right-hand side of the image, we do have the bond log map, which follows, I would say, the conventional method, widely used by most tools in the market. In a nutshell, it's based on the normalized tail energy. It was called NT in the beginning of the tool development. So it's the normalized tail energy of the casing signal, which is influenced by the casing's rear interface. This energy is then normalized to the front face reflection, the sharp increase in the first amplitude, that peak amplitude. So it's normalized to that reflection to provide an estimate of bonding quality. On the other side, so the left-hand side, it's what really sets this tool apart from the competition. That's the micro debonding map. This output is based on the rate of attenuation observed in the casing's back wall reflections. By calculating the ratio of energy decay between each back reflections, the tool provides a sensitive indicator of the acoustic impedance at the boundary right behind the casing. It does offer much more granular insight into potential microanalysis, which was overlooked for so many years, in my opinion. And it's a bit of a shame because that's one of the root causes of the SCP, sustained casing pressure. And we'll dive in deeper into that in just a moment. Yeah, for in terms of interpretation or color coding, can see in the next slide, if you can give me the next slide, Joe, please. We can see how the Nusonix map are coded. So this table presents the recommended color maps and scale ranges for both maps, micro depending and bone log measurements. These ranges have been adjusted using a linear transformation to ensure consistency in interpretation across different data sets. The color coding itself represent the SLG materials, solid, liquid, gas. It is intentionally similar to what's commonly used in the industry. This was designed to ensure a smoother transition when switching to the Nusonix tool for data interpretation. This way, it makes it more intuitive for users already familiar with conventional outputs. This way the transition will be smoother to the Nusonix. Of course, these color maps, along with their recommended ranges and scales, are not set in stone and are subject to fluctuation and interpretation. After all, we're interpreting depending on the conditions and the cement properties. As more data sets are acquired and analyzed, they are likely to evolve to better reflect the full range of field condition. But that doesn't really prevent us analysts for a bit of tweaking according to what we're seeing, well conditioned, different cement properties, and so on. I believe it's now time to go to stay away from the theory, I guess. And I do have a case for you today. We can see together how this tool performs. Before looking at the actual data set, there's a bit of context I want to start with. In this case, the customer wanted to run the Nusonix in an injector well completed with a 5.5-inch liner. And behind it, there's a 7-inch casing towards the upper section. So we do have a dual shrink configuration over a pretty short interval towards the top. 100 meter of perforations between 2004-15 and 2003-15 meters. Was perforated there to allow for a cement squeeze. They aim to isolate a specific formation. I'll talk about the formation in a bit. So according to the perf wash cement standards, we do need at least 50% of 50% of isolation within the target formation for the operation to be considered successful. And it's also worth mentioning that we do have an RBT logged alongside the Nusonix, which is cool. This allows us to directly compare the performance of the Nusonix against the conventional sonic radial bond logs. By the way, the formation is called the Z1 formation here, and it's mainly composed of anhydrite. So yeah, keep that in mind. And yep, let me now take the screen sharing. And yep, should be. Is it working?
Nearly there. I think it takes a second to come up.
Yeah, let's just wait for it. Let me stop and try again. Share. Yeah, I think it's good now.
Yep, thumbs up.
Right, nice. So yeah, as you can see here, this data set includes a lot of tracks and a lot of information, I know. But don't worry, we're going to break it down step by step. I'm gonna focus only on the features of interest. I'll walk you through each of the relevant tracks, and some of them will be probably familiar to you. Others maybe new, but we'll sort it out all together. I'd like to start with two key points. First, as I mentioned, we have 100 meter of perforations, and that clearly is visible in two maps here. If I zoom in a little bit to that interval, we do have eco map and radius map. So in the radius map, we do have those red dots, which represent the channels or the perforations themselves. And next to it, the eco map shows as well, I would say, slots or perforation as well here in lighter color. So yeah, both maps or both arrays are a very good indication of the perforation operation. So that said, the second thing I wanted to talk about is the formation itself. Like I said, it's made of anhydrite, which is well known for being fast formations. And we can clearly see it here. How can I tell? Looking at the video, let me just get it a bit wider for you to better see. Maybe more, okay. As you can see, the VDL and the 5-foot travel time, which I've plotted alongside the gamma ray within the same track here on the right-hand side. You can clearly see in the well-cemented zone, which is about within the perforated section, that the pipe arrivals we can still see here barely disappear and are replaced by earlier, faster formation arrivals that kind of wriggles a little bit. And yeah, these are characteristic signature of fast formation. And that really lines up perfectly with the cement squeeze from bottom to the top here in front of the perforations. Here's an important note here. The tool is not affected by the fast formation because most of the return signal never reaches that formation. So that's a major contrast with sonic logs, which are impacted, leading to higher amplitudes in most cases and greater uncertainty when evaluating the cement quality. Particularly in fast formation like this. So keep that in mind. I've talked a lot actually, but I didn't really explain why this tool is different from the competition. Let's do it right now, actually. There's two curves I want to talk about. And within this track, I want to stretch it a little bit for a better visibility, and I'm going to present the full interval here, right? Okay, so we do have a black curve, the black curve, and the red curve. The black curve is the average micro debonding, or formally named average dec-R. And the red curve is the average NTE, or also now named average bond log curve. So what I like to do is use these curves within the same track because it will give us very important information. In simple terms, the micro debonding curve looks just behind the casing back wall, while the bond log, it looks slightly further into the annulus. And by doing so, by overlaying both curves, we can identify potential microannulus zone. And here how I do it. So in a well-cemented section, which is about here, that was the middle, the two curves should track closely together, which is the case. And if there is a separation or a significant separation, it could indicate a change in acoustic impedance, often due to partial bonding or fluid presence. So let's look closely into this data set. There's, I would say, 3-part here. The upper part, there's a noticeable separation between these two curves. We can look, you can see that both curves are widely separated. And both are below the solid cutoff, highlighted here in blue, meaning that the analysis is liquid filled, not micro debonded. Towards the middle, our well bonded zone. Yeah, the curves overlap, which is a strong indication of good bonding, and that matches our observation of clear formation arrivals. And this is typical sign of well-executed cement job when you see strong formation arrivals or fast formation arrivals. This overlap continues down to around 2000, let's say 30. About 2,437 meters, below which we re-enter in the liquid zone. So significant separation, blue shading. So we're back into fluid again. Interestingly, within this part, the RBT sector map, within the middle part, the sector map here in RBT shows a slightly shallower, what we call it, bottom of cement. So yeah, it ends pretty much here. So within this section, about from 2004-23 meters to 2004-37, like we said, about, yeah, we do have 13 meters of liquid, which is not the case in Nusonix. The Nusonix indicates that we still have cement here. That's probably because of this discrepancy between the two is probably because of the thinner cement, the thinner cement sheet near the bottom of the perforate interval. It does impact the sonic tools because the attenuation of the signal will be decreased. So that's why we'll have higher amplitudes in the sector map. Yeah, I think now it's time to talk about the bottommost part of the log. You can notice probably there's something going on in this sector map which is not replicated in the Nusonix, and those are sense screens. So we do have 1, 2, 3, 4 sense screens installed here towards the bottom. These sense screens appear in the sector map because they attenuate the amplitude, which is common with sonic tools. However, both micro debonding in the bond log map and curves as well, they remain stable, showing that Nusonic maintains data quality across hardware and also pipe weight changes. And that's quite handy because when it comes to interpreting cement behind completion item, it can be challenging. I've processed or interpreted many cement logs, and it's really challenging to assess the quality of the cement behind either weight change or completion items. What I generally do is assume that it follows the same trend of nearby or surrounding areas. So if it's well bonded towards the top and bottom of it, I'd assume that it's probably a continuation. The cement bonding is probably similar to the nearby zone. But with the Nusonix, you can see it right away. It's in front of you. Lastly, I would say don't overlook the pipe inspection channels. They're an essential part of the dataset. They are available to you on both Nusonix and conventional ultrasonic tools. And they're especially useful when trying to understand, unusual features or curve anomalies. Sometimes it's really hard to explain why there's this behavior or this signature in cement map. Well, look back and see, check your inspection curves or channels, maps, whatever available to you. Let me give you a quick example. We do have, I believe, towards the top. Yeah. So yeah, in both cement map and the VDL, there is some attenuations going on there. Here as well in the Nusonix or the cement map. Some something going on from the shape of it. And when looking at the echo and radius map, we can see, we can clearly identify buckling patterns just below the shoe, the 7-inch casing shoe, which also, like I mentioned, it appears also in the cement maps. There's another example here further down in the log. You can notice here this inner wall groove that appears in the eco map, barely visible in the radius map. I can play around with the color map to kind of make it pop, but it's still visible in the eco map, which is, I would say, my go-to map when it comes to pinpointing very thin features. Yeah, this inner groove wall, it is printed in the cement map. Like you can see the bond in the bond long map and slightly in the micro debonding map. So yeah, what I want to say here is the key message here is leverage everything the tool gives you. Every curve, every measurement, every insight can be the missing puzzle piece in your interpretation. And with a tool like Nusonix, it gives you multiple perspective. Your analysis becomes not only more complete, but also more robust. Yeah, so like I said, it's a shame not using whatever piece of information available to you. Also, there's an indication, a curve that has to be checked in all ultrasonic tools is the eccentricity of the tool. It should be kept in under, I would say, a reasonable range. Avoid, or what I want to look at is any change in eccentricity trend. So there is a sharp increase, and it happened here. So if you look at this track, I'm going to extend a little bit for you. If you look here, there is a great or a significant increase in the curve in the tool eccentricity, and that's because of this buckling. It happens. That's normal. When the tool goes through deformations, it will shake a little bit and it gets the tool off center, and that's another indication of features that could be falsely interpreted into something else. And yeah, I think that's a wrap for today's walkthrough.